type theory, and the question is, can we gain something for co-induction?
Yes, thank you, Andreas, for the introduction. So this is joint work with Rasmus Mogelberg, which is also here. So first, some quick introduction. So as most of you most probably know, multi-level type theory can be seen in two ways. So either as a very expressive programming language with dependent types, and also as a foundational system for the development of constructive mathematics. And because of this duality, it has been employed as the basis for a number of proof assistants, such as Coq or Agda. And they have been employed for a big number of formalization and verification efforts. In a lot of these efforts, one is interested also in verify properties of processes. By process, I mean something like possibly non-terminating programs or reactive programs. And in type theory, these things are usually represented using coinductive types. And systems like Coq or Agda, they offer support to the user for programming and reasoning with coinductive types, but sometimes this support is limited, and programming and reasoning with these things is kind of difficult. And I'm highlighting here two reasons somehow for why this is difficult. The first reason is because we have to ensure the productivity of data of coinductive types, so meaning that finding and folding of the recursive definition must be computed in a finite time. And another issue here is with the notion of equality. So processes come with a natural notion of equality, which is the notion of bisimilarity. And this usually doesn't match with the notion of equality of the host type system, which is usually some form of propositional equality. So in order to fix the first problem, several efforts has been done in the recent years. So, and I present here here are two possible ways of solving this issue using encoding productivity in types. One is size types, and the other is guarded recursion. And in this talk, I will focus on guarded recursion. And the main contribution, so what I will try to present here is trying to solve the second problem using guarded recursion, so this mismatch, or working towards solving this issue. So this is the summary of the talk. So what we did is to try to develop a new type theory called Ticked Cubical Type Theory. So this is an extension of cubical type theory with the guarded recursion. This is something that, it's a variant of something that is kind of already been done, which is something called guarded cubical type theory. And for the purpose of this talk, you have to consider cubical type theory mostly as just an implementation of homotopy type theory. Okay? So I need the concepts like the right extensionality principle for functions and propositions and higher inductive types. Okay? And the results I'm going to show you is that for a class of types called guarded recursive types, which can be considered as a first approximation of coinductive types, I'll show you how in a minute, bisimilarity is equivalent with the notion of path equality, which is the notion of propositional equality of the host type system. And this, as I said, this is the first step towards proving this for coinductive types. And I also show how to program and reasoning for processes and how nice and simple it is in this type system. So first, a quick introduction to guarded recursion, if you haven't seen this before. So in guarded recursion, we extend the type system with a modality we call later, is this triangle here. And elements of later A, you can consider them as elements of A that are available only one time step ahead from now. Okay, so this is used for introducing time delay at the level of types. Oh, this is something that shouldn't happen, I guess. All right. Yes, here we are. Sorry about that. So the later modality comes with a fixed point operator over there. And as you can see, this takes a function from later A to A and produces something in A. And function from later A to A can be considered as some of productive recursive definitions, right? Because now the recursive variables occur only at elements of later A, which are available only one time step ahead from now. And there's also this operation next that embeds elements of A available now into elements of A available one time step ahead from now. So using the fixed point operator, it's possible to define this class of guarded recursive types, which are like recursive types, but now the recursive variables only occur guarded. So you mark with the later modality the recursive variables. So for example, here we have the type of streams, and they satisfy this type equivalence here. So these are streams of natural numbers, and you can see that now the tail is always available, not now, but only later. And these are the two, fold and unfold are the two functions that are underlie this equivalence. And as a basic example, we have the type of the stream of zeros, constant stream of zeros, that can be defined in this type theory as follows. So using the fixed point operator, so it's a fix of lambda x's, and then you just apply fold to 0 in x's. Okay? And there's something to notice here is that this is not the usual coinductive type of streams, and the reason is because we have the later modality in the type equivalence there. So the usual type of streams will be in such a way that the tail is available also now. Okay? But using Atkin-McBride techniques, one can encode coinductive types using this implementation of streams here. But this is not part of the talk. So we're going to focus only on guarded recursive types, not coinductive types here. And so streams are usually a very basic example of processes. But in here, we'll try to consider another more interesting example. And we'll try to define something like non-deterministic processes, where the non-deterministic is finite. And usually to represent in type theory this kind of, or in set theory even, to represent this kind of processes, one need to encode the finite power set functor. So a functor that given applied on a type returns the subset, the finite subsets of this type, of elements of this type. And this can be done in homotopy type theory using higher inductive types. And yeah, we had an introduction to higher inductive types before, so you can consider them as inductive types where you don't only have generators for the elements of the type, but also for the identity types of the elements of this type. And this is how you do the finite power set functor over a type A. So you have three constructors for the subset. So you have empty subset, singleton subset, and union. And then you have equality, specify how this operation behave, and really specify that this is the set of finite subset of A. And for example, the second one, you have associativity, right? And then you have idempotency and so on. And using this, you can define, so if you work in a type theory that allows the possibility of having these definitions, you can introduce guarded recursive type of processes that satisfy this kind of type equivalence here. So these are basically like, this thing arises usually when in the study of label transition systems, right? So with finite branching of end labels in the type A. So this type proc here corresponds exactly to the final semantics usually of this label transition system. So right, the type consisting of all the runs of the label transition system. And as an example here, we have we consider a type of booleans for the labels. And then we have this label transition system with three states, x0, x1, and x2. And we can define the processes associated to the LTS. And I'm using the same name here, so still x0, x1, and x2. And this can be defined, as you see in the bottom here, as formally as a guarded recursive function. So it's a fixed point of a map of this form. So it takes triple of processes later and constructs triples of processes now. And then the processes satisfy this type, the propositional equalities here. And you can see that, for example, first we construct the set of the subset of successive states, right, together with the transition. So, for example, x0 as transition f to x1 and transition f to x2, right? So, and we have to mark that the successive states appear only one time step ahead from now. So we use next in here. And then we use fold too, because this is the right to left morphism underlying the equivalence up there. Okay, so now we can put next to the first LTS another LTS, and one can actually then start defining a notion of bisimulation and bisimilarity for LTSs, and it's possible to prove, for example, that x0 is bisimilar to y0. So in this example. But even before started talking about bisimulation and bisimilarity here, we can indeed in our type theory we can directly prove that x0 is propositionally equal to y0, and we can do that by first proving a lemma, so proving this 4 equalities simultaneously, and in the end this will actually correspond to constructing a bisimulation, right? So the pairs in these equalities are from a relation which is a bisimulation, and therefore that's how you will usually prove that x0 is bisimilar to y0. And this uses a lemma here, which is an extensionality principle for leta A, right? So this says that if you want to prove that next of x is equal to next of y, so then this is the same as proving that x and y are equal later. Okay, so how do you use this? Let's see how to prove this, the first lemma. So we proceed by Gaussian recursion. So we assume that the statement holds later, and we want to prove that the statement holds now. So in here, I'll show how to prove that x0 is equal to y0. And so since, in particular, you know that by assumption that later you know that x1 is equal to y1, then by the extensionality principle we've seen one slide before, you know that next x1 is equal to next y1, and therefore you have this second equality here. Similarly for next x2 and next y1, right, using the extensionality principle. And then the third equality is just the idempotency of the union, and then the first and the last equalities, these are just by construction. And then you do the same for the other. So this is it's very nice, it's very simple, a way of proving bisimilarity somehow, but you directly prove propositional equalities. So now let's try to make things a bit more formal. So let's try to define the notion of bisimulation for processes and bisimilarity, and our goal is to show that bisimilarity coincide with propositional equality here. So start with a relation on processes, and you say that this is a simulation if whatever two processes are related, and the first process make an A transition to x prime, then the second process also make a transition to y prime, and then you would like to say something like that the new states are related. But in here, we hit a wall, because somehow we don't know very well how to express this, because you have a relation that relates states right now, but processes right now, but x prime and y prime are states that live only one time step ahead from now. So in order to solve this, we have to import some technology from a type theory called clock type theory, in which they use a tool called ticks. And so what we do is basically this is our type theory. So you take a cubical type theory and you extend it with the notion of ticks and rules for this tick. So a tick is evidence that time has passed. That's how you have to consider this. So and now the later modality is indexed by ticks, and you can see, for example, on the fourth law that you can take a term in this type, in the later alpha tick A, so meaning that this is available only one time step ahead from now, but you can open this term and obtain something in A if you have a tick in your context. So if you have evidence that time has passed, you can use the evidence and apply to the term to this evidence and obtain something in A right now. This is not too different from, for example, this you can consider still also this as a dependent function space, or not too different from also the path types that Evan was describing before. And you can write later A if the tick is not free in A, and you can have now, for example, next is very easily definable. It's just lambda x, lambda alpha x, right? So just very nice. And then you can go back to the bisimulation, and now you can fill the holes, the question marks that we had before, because now you can say, well, how to relate states one time step ahead from now. So you can just say, well, this you have a tick, you use the later modality, now it's indexed by a tick, you have your tick in a context, so then you can apply R, and you can actually also apply the x prime and y prime to the tick, obtain something in proc, and then relate them with a relation. So then you can proceed with the usual definition of bisimulation here. So you can say R is a bisimulation if it's both it's a simulation and its opposite is also a simulation. And then by Gaussian recursion you can define bisimilarity as the greatest bisimulation. And it's nice, you can directly prove this nice statement that for two processes x is bisimilar to y and x is equal to y are equivalent types. So as an extended example, we also considered CCS, so the calculus of communicating systems. So this is with the grammar, and we have a restriction in that we consider so we have recursion, but we only consider the recursive variable to occur under an action. And you can implement this. So this is kind of, we have the implementation that it's basically a Gardner recursive variant of CCS. And then you can define an operational semantics. This is basically defined as an LTS. So this is a coalgebra of this form there. And you can associate, therefore you can associate to every process, to every CCS expression, a process, basically using basically fully evaluating the expression using the operational semantic. And then you can prove theorems like that given to expression in CCS, then P is bisimilar to Q, then is equivalent to saying, to proving that the process associated to P is equal to the process associated to Q. And in here, I didn't tell you how to define bisimilarity here or bisimulation, but you define, before I told you how to do it for processes, you do the same for this kind of coalgebras here. Okay, maybe I don't have much more time, so this is, I'll jump to conclusion, but so I presented you a type theory called Ticked Cubical Type Theory, where you can prove that bisimilarity is equivalent to path equality for Gardner recursive types, and at least I showed you for processes, and I hopefully I was successful in showing you that how nice and simple it is to do equational reasoning for processes in this type theory. And there are so the example of processes is just an example, and actually you can do much more. So we have a generalization. So as I already mentioned, so you can define bisimulation and bisimilarity for general coalgebras in this setting, as one usually does in category theory, let's say, and then you can prove that for the finite coalgebras, you can define a notion of bisimilarity exactly for the finite coalgebras, and this coincides with equality in the finite coalgebra. And the finite coalgebras of functors in this setting correspond exactly to Gardner recursive types, right? So you have this for this principle for all the Gardner recursive types. And then we also have the notational semantics in the categories of they call cubical trees, because these are presheaves, contravariant presheaves over the category C times omega. So C is the category used for modeling cubical type theory, at least in the style of Coq and others. And omega is the category of order natural numbers. And this is a model that also already been used in Gardner cubical type theory. And then future work, so we would like to explore a bit more with up-to techniques. And the main challenge is try to extend this to coinductive types. And there are some complicated challenges there. And last but not least, of course, we would like to have an implementation of this to try to play a bit also with it and see what we can do in it. But okay, thank you very much for listening.
Right, we have like 5 minutes for questions. So there is an anonymous question on Slido. Is there a way to reason or about or prove bisimilarity using up-to techniques?
Right. So we still haven't investigated these possibilities. We know that Niels Anders Danielsson has done some studies in this direction using size types in Agda, right? And our idea would like to see what can we say. I mean, if it's a way of replaying the game he played in this type theory and see if similar things may hold for Gardner recursive types. But we haven't thought that much about it. Yeah.
Good. Here's a question.
I hope I didn't miss it during the talk, but could you say a few more words about the need for cubical type theory? You said extensionality principles, but that was...
So yeah, so what we need in here is stuff like functional extensionality and propositional extensionality that follows from univalence. Why do you need this? Yeah, I think I will have to go a bit more technical here, so maybe we can discuss this later. Yeah.
There's questions from Max New. Is there an implementation of tick type theory, and is the later modality monad?
Okay, so first question is, I think there is no implementation. And the second is no. And actually, it's something you don't want. So you don't want the multiplication. So you have what you want is the structure of applicative functor, actually. Yeah, you don't want this to be a monad because you don't want to collapse multiple time step into one, right? So you don't want to say that something living 2 step ahead from now lives also 1 time step ahead from now. So this will kind of collapse the whole future time steps into one. Yeah.
Ambush?
Is it true for normal cubical type theory that bisimilarity and equality is the same for coinductive types?
All right, so you can encode coinductive types using this Arendt's, Capriotti, and Spadotti way of doing things, and they also proved that at least there is a conduction principle, so that at least the two are logically equivalent. So the difference is that they only do it for non-well-founded trees, while we, at least at this level, would for the recursive type, this holds for all possible functors. And the second thing is that, right, so what we have is an equivalence of types, really. So this will, in principle, hold, for example, if you have processes, some LTSs where you have additional structure also. It is not like, so the set of successive states is not just a set, but in principle can have even higher structure. We don't have example of this thing so far, but yeah, it's a bit more general. It's just a bit more general, yeah.
Right, then I think it's time for lunch. The most hungry people already rushed out, but let's thank Nicolo again.
Thank you.